All right, let's solve the 1D Poisson equation. We already know the Poisson equation in electrostatics. This rho, we assume epsilon is 1, supposed to be rho over epsilon. We're going to solve on a unit bar, like on a unit rod, a rod of 1 meter from 0 to 1. And we assume that the potential exists only within the rod. It doesn't exist at the end. And therefore, psi of 0 and psi of 1 are 0. We are going to, like I said, assume epsilon 0 is 1. The density is 1 for simplicity. Length 1 rod. And we are going to have 5 nodes. We're going to have 5 nodes. That's 0, 1, 2, 3, 4. So we're going to have 5 nodes, which is counting from 0 to 4. And when you have 5 nodes, that means you have 4 elements. From here to here, 1. From here to here, 2. From here to here, 3. And from here to here, 4. So let's define our parameters. L equals 1. That's the length of the rod. There's no need to define rho over epsilon, or if you want, you can call it rho equals 1, epsilon equal 1. And so rho, or I can call it just the right-hand side, f of x equals rho on epsilon. And I now need to divide the length into nx. So I'm going to make nx to be 5, so that h, which is the interval, would be L divided by nx minus 1. Why minus 1? Because you have 4 elements. So you cannot divide L by nx. It has to be nx minus 1. Then we have x itself. Of course, I'm supposed to import the important tools. Import numpy as np for numerical calculations. Import matplot library .pyplot as plt. That's for plotting. So I can now say np dot linspace. I want to divide the interval from 0 to L into nx. Then I run this. It runs successfully. Now I think I have everything I need. Now let's move on to the matrix. There's the stiffness matrix. We already have seen how to develop them in the lecture. So the stiffness matrix is each element will contribute this. And the global matrix is going to look like this. And the right-hand side, the F. But in our own case, Fx is just 1. But anyways, the load vector or the force is like this. So it's h over 2 times F, which is just 1. In essence, it's just going to look like this for the 5 nodes. Sorry, for the 5 nodes, yes. So 1, then 2, 2, 2, then 1. H over 2 here. For the K, because we have 5 nodes, we're going to have the matrix look like this, 1 over H. So we are going to, the task is to develop this matrix, the global one. So what do? We can We can start here, I think, in this cell. So first, we want to develop the diagonal, this one, this main diagonal. Can use a function called, so we can call it main equals np dot full. So I'm going to generate a full row vector. Full. I'm going to populate this full vector with 2's. Later, I'll change this to be 1 and this to be 1. So let's make it full. Size nx. I'm going to add 2 to it. So what does main give me? Main gives you this matrix 1, 2, 3, 4, 5. But I want to make the first element and the last element, but not yet, not yet. So I would like to make this a diagonal matrix first. Anyways, let's make the first element 0 equals to the last element. Let's make it 1. So that I can have now 1, 2, 2, 2, 1. Let's call May and see what we get. Good. Now I want to make it a diagonal matrix. np.diag May. So I want to make it a diagonal matrix. So now May is a diagonal matrix. So I successfully built this one. I need to build this off diagonal matrices. So let me call a matrix vector off. So let me call off equals np.full. But in this case, because this is the length, you see the length of the off diagonal matrices can never be the same as the main one. So we are going to generate off nx minus 1, that's the length. Let's fill it up with minus 1. So we're going to fill it up with minus 1. Let's see what off looks like. Off will look like this. Now we want to, there is the off that is going to be in the top, and there is the off that is going to be in the bottom. So you can define the top matrix, top, np dot, we can make it a diagonal matrix of the off, but in this case, off above, that's the one you see here is telling you that it's off diagonal, but it's on the top. I have to write the G here. So when you look at matrix off, you will see it like this. So I'm going to do the bottom as well, or I call it down, equals np dot diagonal matrix off, but in this case minus 1. And so here, if I used 0, would be the same thing. If you used 0, would give you the same May, or if you leave it empty, it's automatically going to catch the diagonal, the main diagonal. But if you want to decide where the values should be, you use these indices 1, minus 1. So this is very important. So now we are going to have 1 over h, right? So let's first develop K. So K matrix is top plus down plus main. Let's see what K looks like. So what we have here is K looking like this. This is our K matrix, which is exactly this. Okay. So what we need to do now is we need to multiply it by 1 over h. So k is k, or I can say 1 over h times k. So let's see what k becomes. So k becomes this. Now we have what we want. Now let's go for the F matrix. The F matrix is h over 2, 1, 2, 2, 1. This is easy. So F equals np dot full. So what does this mean, dot full? It's just like, get me some len nx and fill it up. Get me some row vector of len nx and fill it up with for example, 2's. So now I'm filling it up with 2's. It gives me this, but then I want to change here to be 1 and here to be 1. So I do the same thing I did here. F of 0 equals F of minus 1 equals 1. Then here I say F equals h over 2. I have to say h over 2 times F. So let's see what F looks like. So this is what I have. This is what I have. Now I have my stiffness matrix. This is the K, and I have my my load matrix. So how do I apply the boundary conditions? The boundary conditions is psi of 0 equals psi of 1 equals 0. This is trying to tell you that the value here and the value here. So when you generate the psi, it will be only for these guys, but it's 0 here and 0 here. And therefore, and also the same applies for the K. The K, you come to see that you cannot multiply the K by a vector that has 0 here and 0 here, because we're solving for ax equals to b, and you're multiplying the a is the x is the vector for the psi, and it's 0 here and 0 here. So you can only use this region because it's zeros everywhere. So we therefore have to ignore the both ends of matrix F and matrix. So we can say K inner is K of 1 through minus 1, comma, 1. So this is for the rows. We're going from row 1 until the second to the last. And then column 1 until the second to the last. So column 1 through minus 1. And F inner equals F from 1 through minus 1. Python counts from where you want it to count, but it will go one element before, because we have seen it counts from 0. And therefore now we can so what is there any? Okay, so I think this is where I just apply my, okay, so now I have this, and now all that is left is to solve for sine. So it's solved for sine. So psi, it's going to be some numpy dot zeros of size nx, but eventually the inner elements of psi. So psi inner equals np dot. So this is the inner ones is what we use these guys to get. right? Yeah. So linear algebra dot solve K in F in. Yeah, so we run this and we are going to add this inner psi to the main psi. So psi of 1 through -1 plus psi inner. And this is our solution. This is what we get. Now, the analytical solution, let's see if I wrote the analytical solution here. Okay, so if yeah. So if I can remember the real analytical solution is, if I can remember properly, the real analytical solution is 0.5 times x times 1 minus x. That's the analytical solution for that very problem. And if we run this, what we get is okay, so let's call this analytical solution. And this is the numerical solution. Specifically finite element. So what we can see is they agree. And that's the finite element method solution for Poisson equation. We solved for only 5 nodes because this is what we have in the lecture notes. But you can play around with it.